And welcome to my presentation for subject XNB272, a biomechanical analysis. So the movement I have chosen to analyse today is the standing long jump, and the biomechanical goal of this movement is to maximise horizontal displacement of the body's centre of mass. Performance is determined by how efficiently the athlete generates ground reaction forces, impulse, and the optimal takeoff angle. So here I've done up a deterministic model. The deterministic model links each biomechanical factor to the final horizontal distance or displacement of the center of mass. The horizontal distance is influenced by both takeoff angle and takeoff velocity. Both of those factors are determined by the amount of impulse, which is created through ground reaction forces. The amount of ground reaction force is influenced by the time of force production, which all comes down to the flexion of the joints. And how low they allow the body's center of mass to get during that counter movement squat. So the lower and more flexed the body can be during the squat, the more time we can spend extending our joints and projecting the body's center of mass off the ground into the air, creating those forces that will basically determine the end distance. So now I'll get into a few variables that will increase or decrease the overall performance and horizontal displacement. The first variable I've chosen to look into is the whole body positioning at takeoff. So the whole body and center of mass wants to be substantially low during that counter movement squat with the hips, knees, and ankles flexed so that once they go into extension, they've got time to generate high ground reaction forces and a larger impulse. Some common errors you may see that will negatively impact the horizontal distance at the end of the jump is an excessive forward lean through the trunk. This may shift the center of mass ahead of the feet, which could reduce both the vertical and horizontal ground reaction components. Also inadequate hip flexion and knee flexion, which just means you won't be creating that same amount of ground reaction force and won't be able to go as far. Another important variable in the standing long jump is the upper body coordination. So the arm swing and upper body coordination do contribute quite significantly to the impulse of the jump. A symmetrical backward counter movement arm swing followed by a rapid forwards and upwards arm swing increases the whole body's momentum. When both arms also swing in sync with the lower limb, they elevate the center of mass and transfer that momentum forwards. Common errors include insufficient backward swing or also when the arms swing asymmetrically. So that can cause quite a bad trunk rotation, which will reduce that forwards momentum and probably destabilize the landing as well. Proper coordination just ensures that the upper body motion complements the direction and the momentum of the jump rather than opposing it. Another important variable that I've chosen to look into quantitatively is the counter movement squat knee flexion angle. So basically the knee flexion angle determines the depth of the counter movement squat, which also determines the time available to apply the force. A deeper angle basically increases the impulse and ground reaction forces, whereas a shallower angle just limits that loading time, which limits the ground reaction forces. Previous studies did show us that the optimal angle is between 29 to 38 degrees of knee flexion. However, more recent studies show a more broad recommendation, which is just less than 45 degrees. You do want to ensure an optimal angle as it does allow effective use of that stretch shortening cycle. So it just basically allows your muscles to produce that strong concentric contraction while not losing energy through excessive depth and still creating an optimal amount of ground reaction force. The last variable I looked into is the takeoff velocity. So the takeoff velocity basically reflects the combined horizontal and vertical components of the movement of the center of mass. The velocity depends on the magnitude of the ground reaction forces once again, and its direction and duration of the force application. An explosive triple extension through the hips, knees, and ankles with an optimal forward-leaning trunk will allow greater horizontal projection of the center of mass and quicker velocities. When you see the lower velocity values, they usually indicate a limited rate of that force development or an overly steep takeoff angle, which would reduce the horizontal distance overall. To observe and analyze the movements, it's important to consider the following factors to ensure that we get accurate results. A few I have listed here is the filming quality. So this can include having a camera on a tripod so it doesn't move around, impacting any markers or distance tools that we use in the software. Also using a correct frame rate speed. So for my observation, I use just a slow motion on an iPhone 16 Pro which is around 120 frames per second. And then once I popped it into Canovia, I slowed it right down to 240 frames per second. Joint markers are another great addition to make the tools on Canovia more accurate, and it allows you to reproduce accurate joint angle analyzations when you're taking multiple videos. That also goes hand in hand with clothing choices too. I think it's best to wear plain, tight clothing that's easily visible against the background. Having a clear, plain background and good lighting setup is important to ensure everything's just easily visible and the attention is easily directed to the subject. And then the software that you use to analyze the movements. So I use Canovia 2D motion analysis, which studies have confirmed the reliability and validity of Canovia as well. So when used correctly, it can provide accurate, repeatable data for both qualitative and quantitative assessments. Observing the footage of my athlete's jump, I found that her whole body position showed a medium amount of flexion through the hips and knees. Her trunk was leaning forwards and her head was positioned nice and neutrally to her body. In regards to her upper body, we can see a really nice backward arm swing during the counter movement phase, followed by that forward upward swing during takeoff, so that looked really good. And it also appeared that her arms were moving in sync as well, which is great for avoiding that trunk rotation. Quantitative analysis I did on Canovia for her knee flexion angle. I found it to be approximately 70 degrees at the lowest point of the counter movement squat. However, when I reviewed the literature, the optimal ranges are obviously below 45 degrees, which demonstrates that her counter movement squat may benefit from some attention. I analysed the takeoff velocity of my athlete. So to do this, I basically got that footage from the sagittal plane and used the human tracking tool in Canovia, and then I tracked her body's displacement of the centre of mass during that takeoff phase. This produced approximately a velocity of about 1.6 meters per second. So overall, the observation of all the footage, it showed that she had good upper body and arm swing coordination and a nice neutral head, but I did find she had slight limitations in the hip and knee flexion and also her trunk control during that loading phase of the counter movement squat. I believe these would have negatively impacted her total impulse and ground reaction force production. Broken it down into 3 main areas of where I think she could benefit from some attention. So first, the inadequate knee flexion during her counter movement squat. I believe that it just wasn't quite enough, and it also didn't sit within that range found in the literature, which would have impacted her total impulse, reducing the takeoff velocity. She did have quite an excessive forward trunk lean, which would have shifted the center of mass ahead of the base of the support, which directs the force less efficiently and compromises the force direction and production. Also, the limited hip flexion probably played quite a role. This would have reduced the time of force production, lowering the ground reaction time and impulse pretty much the same as the knee flexion. So altogether, with all of these faults, I think they would have restricted both the vertical and horizontal components of the forces and impulses created, which would have decreased her total jump distance. To address these faults, the athlete should aim for slightly deeper knee and hip flexion, below 45 degrees to lengthen that ground contact time, maximizing the impulse. During the counter movement squat, the trunk should remain a little bit more upright, only leaning forward during that extension just to improve that forwards momentum. And increasing hip flexion will also enable a greater stretch shortening utilization and improve the takeoff velocity overall. Wraps up my biomechanical analysis on the standing long jump. I appreciate your time. Thank you for listening, and there's the list of references that I used there. Thank you for listening.